everyone. I'm Noam, I'm from Bar-Ilan University. I'm going to present my work about predicting human strategy decision using facial expression. This work is a joint work with my colleagues, IJCAI that is here, Yossi Keshet and Tzarik Klaus. So you can ask all the questions to Shem, if you like. This talk is, as you can see, it's all about prediction of human strategic decision, only with their facial expression. Okay. So let's dive into a video from a film. You can see a poker film. And what we want to do, or what we did in this work, is according to a video of like that, not a picture, full video of the face. We try to predict what it's going to do. For example, in poker, what card does it have, or what it's going to do. You want to get another card, want to do something. So it's really important, especially in games like poker. In poker, it's even more challenging because the player has incentive to hide their intention. They don't want you to know what card they have. So instead of poker, it would be nice if we did poker, but instead of poker, we try to start in a much simpler game. This game is a variation of the centipede game, if you know it. The variation is because both players take their decisions simultaneously. Okay, so in each round, they have to decide if they want to stay or leave in the game, and they do it simultaneously. So, for example, if both players choose to stay, you can see there is a nice piggy here that there is the money in the pot. Okay, so if both players choose to stay, the money duplicates. If they both choose to leave, the round will end, and they will split the money. The nice thing, what happens if only one player chooses to leave and the other player wants to continue to play and wants to stay in the game. So this buster gets all the money. Okay? The game ends. So this is really important property of the game because the decision has a cognitive meaning. Okay? If you want to leave, it means that you're going to do something that is not really nice to the other player. You're going to take all his money. So the main task in this game is to look on the face of the other player and try to predict if he's going to leave. Because you really don't want to stay in the game if he's going to leave. If he's going to stay, or you think he's going to stay, maybe you should stay because you want more money. In game theory, in the centipede game, the original centipede game theory tells us that you should leave on the first round, right? But if you leave in the first round, you don't get anything, almost anything, half a euro in this case. So first we examine the case in our variation of the game. This is the normal form of the game. As I said, the one that leaves takes all the money. If both leave, they split. If both stay, continue to the next game. This game has a finite horizon. So after, let's say, 10 rounds, the last round is a special case. The game ends no matter what. So if both players stay, they split the money like they leave case. So in this case, it's really easy to see that the dominant strategy is always to leave, no matter what the other player is going to do. So the round before the last, now we know what will happen in the last round. Both players will leave. So they will get half of the amount of the last round. And again, leave is the dominant strategy, like in the original centipede. So using backward induction, now we can tell that, like in the original centipede game, one must leave directly on the first round. But people don't act like that. Most people stay, let's say, 5, 6, 7 rounds, and then they choose to leave. So the big question is, the other player is going to leave or stay. Now I show you 5 seconds of video of one of our subjects, and you have a task. You need to try to predict what she's going to do, leave or stay, only according to their face. She looks on the screen, do nothing, and now she made a decision. What do you think she did? Yeah, it's really hard to tell. This time she stayed actually, but it's really hard to tell. This is the nice thing. And not as like many other AI tasks, we gave this task to normal people, like us in the lab, and asked them to see videos like that and try to predict what to know how much normal humans are good in this task. We presented them 1,800 clips like that. They sat for hours and just try to predict, and we didn't pay them any money. And the nice thing that they were even worse than chance level. They were quite good in the state prediction because most of the time players stay in this game, but they completely didn't know how to predict the leave action. And this is what's important, because if you miss the leave action, if you tell all the time stay, you won't gain any money. So predictors that stay all the time have quite good accuracy, something like 8% or 80% or something like that, but agent that we play according to this predictor will gain 0. Okay, so it's really a bad predictor. We use a software that tracked 66 facial points over time. Okay. You can see me here. The black dots are the facial points that the software tracked. First thing we did is to calculate two vectors, the nose vectors and the eyes vectors. There is a noise, inherent noise in the system like any tracking system. So we first remove this noise using Kalman filter. Okay? And then we normalize the picture. Why we normalize each frame? Because if the players move and they move a lot, something like that, this is not facial expression. Okay, the points moved, but they didn't do any facial expression. We want to capture only the facial expression itself. So we move the nose in each frame to the center, rotate the head, and stretch it, so the nose will be always 1, the distance, and the distance between the eyes will be always 1, like the nose. Okay? So all the movement now will be only because of facial expressions. This is also help us because different players have different head dimensions. So it's fixed this problem. So after normalization, I look something like that. Here's my nose in the center. And now you can talk about properties or features. So for each dot, you can track the x and the y of this dot over time. It gave us better result to move to polar system, polar coordinates. So each dot, we track the distance from the nose and the angle. So for example, the distance from this point on the eyebrow to the nose looks something like that in one of the rounds. Okay? So if we put now all the data at the same time, this is what we get. We get 66 by 2 channels of time. That is really messy. And we have 4 more time series that we wanted to catch the head movement, because maybe it tells us something that the players did something like that or something like that. So we capture this movement also. So as you can see, we have messy data, and even worse, each round took the players different time. The time varied over rounds. So we can't really use this property to directly into something like SVM classifier, because we need a fixed amount of properties. So the nice trick we did here is to use a covariance matrix. The covariance matrix actually remove the time dimension. And this is the covariance matrix, picture of the covariance matrix. And now each property or each feature is how much a pair of two dots change together. Okay? So we lost a lot of information. Now we don't have the direct movement of each dot, but we can tell how much it's varied together with a different point. And luckily, it gave us enough information. About covariance matrix, as you know, it's a symmetric covariance, so we can take only the upper half or the lower half. And again, it's more than 10,000 of points, so we use PCA. Okay? And we took only the first 10 principal components. That was enough. Another problem was that the data was completely imbalanced, because most of the time player choose to stay. And we needed more leave points. So just to check it out, we used a regular SVM, and we calculated the area under the curve of the regular SVM. As you can see, it's a little bit better than chance level, but it's really not such a good predictor. What he did is to tell us he predict all the time stay. Okay? This is what happened in imbalanced data. So first, we try to use the double loss SVM. Double loss SVM means that there is two different C's. C0 and C1. And you can play with the C's according to how many points you have in each class. It helps a little bit, but not, as you can see, not really good. So we use a max AUC SVM. It's proven that if you have the same amount of points or the same amount of data points in each class, it's maximized the AUC. So the first way, what we did, we just duplicated the data points of the div. Okay, that was the minority class. To have the same amount of data points in live and state. After that, we thought that, okay, in the first three methods, we use cross-validation over subject. But it has a problem, this method, because we couldn't use the history of the con player. Because cross-validation over subject means that now the test is the con player and the train is the other player. But you can't use the history of the con player. So we moved to another type of cross-validation, which means leave one out. Now the test is only the current player round, and the train is all the other players and the history of the current player and his opponent. Because maybe his opponent's history can tell us something about what this player is going to do. And as you can see, it didn't really help. So we tried to do undersampling instead of duplicating the minority class. Now we undersampling the majority class. It was a little bit better. And instead of duplicating, we used the smart algorithm that just creates new synthetic data of the minority class. And we get something like 0.6 AUC, which is not really good. So what we thought that maybe the history has an important role, but during the time, maybe the prediction improved. Maybe we should give a player to play a little bit, and after, let's say, 50 or 60 rounds, the prediction will be better. So we try that with the methods of the class with history. And as you can see, in the x-axis there is the history length, which means, let's say, the point of 60. It means that we took only rounds with at least 60 rounds history length. It's like and then you can see that the accuracy improves a lot in the beginning, and hence some kind of status quo after 60 or 70 rounds. After that, it's only garbage because we didn't have enough rounds with such a history length. So now we thought, okay, maybe the AOC will improve if we will take only rounds with at least So again, the nice AUC. And now I will remove all the rounds that have less than 70 rounds of history length and try to predict. And as you can see, the accuracy improves a lot. The class history method gave us 70% of accuracy here in this point of both classes, which is, I think, quite astonishing, because people were really dead in this task, and our predictor succeeding 70% of accuracy, which is far better. Okay, what we want to do now? Now we want to try something that is a little bit more like poker. We tried another game that's called the liar game, something like that you have to put cards upside down, and it should be, the number of it should be one more or one less from the card that is here on the table. But you can do whatever you want, you can lie. And the other player can try to catch you. So we want to know if the player is going to put the cards that he claimed. Is it a true claim or a false claim? Another thing, to conclude, the novelty of this work is one of the first works that we predict the strategic decision according to the facial expression when the player has incentive to hide the intention. Okay, like in poker, they don't want the other player to know what cards they have. And it's the first work that uses the cross-validation to overcome the variety of the timeline. Future works that actually I'm starting to do right now is to use brain activity. It's really nice to predict what people are going to do according to their face, but it's really cool to know what they are going to do according to the brain activity. Because we thought that maybe we can do it according to the face expression, maybe there is enough information, but we know that there is enough information in the brain. I don't know if you can read it, but it can be really cool. Another thing is according to body language. That would be really nice. We want to use the Kinect for that. That's all. Thank you. This is my virtual me. Thank you very much. Questions?
Is it working?
Great talk, thank you. So if it's really hard for the people to tell, how did the algorithm tell? And if you had some experts, not normal people, but experts, would they come up with the same set of features that the algorithm has found?
I don't think that the experts will come out with the same features, because our features are how two pairs of dots vary together. I don't think that experts calculate covariance matrix, but it's really good questions, because this is exactly what we want to do. We want to give something like poker players, someone that this TV Light to Me TV series, someone that is really good in lie detector with someone like that, and see how he is going to do that task. What could be really nice question. Another thing that we want to do is to find out more interesting features about our method. For example, we really wanted to be able to tell that, okay, about you, when you played, you move a little bit this eyebrow when you live, when you choose to live. That would be really nice. We want to do that.
So when you looked at the covariance features that were salient, they were found to be salient, did they make sense like that? Is it like the eyebrow moves with the...
To tell you the truth, we haven't really looked on the values of the covariance matrix. We want to do it now. That could be interesting, and it could be interesting because, as you can see, there are not many values that are above 0. So maybe we can do better.
More questions? I'm not sure where I read it, but I think concerning this brain detection, I think there was a paper published not long ago in which about the decision-making process. Apparently, before the decision is made, a few hundred milliseconds, the brain set in a particular position. So that makes it- yeah. So couldn't you use that to reduce the window or kind of focus better on which is the moment in which perhaps there is a coincidence between the facial expression?
Yeah, exactly. One of the problems we have now that we don't know when the player made his decision. We have something like 5 or 10 seconds, and maybe, as you said, that the aha moment was after 8 seconds.
Yeah.
If you could know to take only this window, it would be really nice. And the aha moment, they use fMRI, I think, for that.
Yeah.
And the problem that you can see the aha moment, but you can never tell exactly what happened there, because you can't ask the subject what happens in the aha moment. But it's unconscious. He doesn't know that about this aha moment.
But you know when the decision is made about leaving or
We
staying.
think that we know, yeah. One of the things that I'm trying to do now is to capture the net signature about this aha moments. Nobody has done that in something like it's better than fMRI, for example, MEG, MEG. That could be really interesting.
More questions?
In your experiment, was there any cases when people, before they make decisions, they switch between decisions and many times before they decide what to do? How does that influence your?
How do you mean switch?
Maybe before I finally decide to leave or stay, I will be torn between decisions.
Maybe this is exactly what we don't know that. If you plug in EEG or fMRI, maybe we don't know that. And now that you ask, I remember one couple, the only couple, there were 2 couples in the outside game. And they were the only couple that chose to stay all the time. So another interesting thing to know in advance is how well these 2 players know each other. Because there are players that could establish some kind of a cooperation between them and decided that okay, it's a smart thing to stay. And there are players that don't, that didn't do that. So and now I'm trying to do it all over again and ask the correct question before that. How well you know each other? Are you a couple? Do you hate the other player? Something like that. That could help us.
So there are also studies about, is this working?
No.
Hello? So there are also some studies that show that giving some particular chemicals, people behave in a more generous or less generous way. So is that, do you think that's something that could relate with the facial expression as well, or not, or is totally independent? So I mean, you know the examples in which in the ultimatum game, I mean, people behave much more generous if they give, I think it's oxytocin. They made experience with women and they were much more generous.
Yeah. Even smoking drugs.
So you don't think that could be also
I think, not from my experience, but I think that people that want this thing, maybe they have more relaxed facial expression also. I think that would be interesting. And about that, one of our future work of Moshe, my friends here,
he didn't answer any question, by the way.
no, is to use this virtual player to change his facial expression that the other player will think that he's going to stay.
Okay, good. So,
Without any chemical reactions.
okay. Any more questions? So thank you again. And the session is over.